a probability-guided sampler for neural implicit surface rendering. Reconstructing 3D structures from multi-view images is a core problem of computer vision. In the last few years, NeRFs emerged as a promising alternative for 3D reconstruction by utilizing volume rendering, which enabled dense reconstructions. NeRF introduced a new view synthesis strategy based on volume rendering. During training, projection rays are uniformly sampled from the image. Image synthesis is achieved by rendering sampled 3D ray points. NeRFs do not impose sufficient constraints for representing 3D surfaces. On the other hand, neural implicit surfaces with NeRFs solve this issue by learning an implicit representation of the foreground surfaces during training. This learned representation enabled reconstructions with finer details and higher resolution of 3D surfaces. Additionally, previous work showed that 3D regularization using 3D data during training improves reconstruction. Many existing methods focus solely on guiding the sampling of 3D points along projection rays, disregarding pixel sampling. This leads us to argue if the full potential of neural implicit representations is being explored, which leads to the research question: can the implicit surface representation guide training rays and points for accurate 3D reconstruction and rendering? A schematic of our approach is shown in the figure to the right. Our main contribution is a probabilistic 3D orthographic image projection sampling that is view-dependent and feasible for training. We propose a new loss function that improves foreground and background modeling by combining near the surface and empty space components. Further, our method is agnostic to the implicit model, allowing the proposed sampling to be used with different backbone models. We demonstrate this versatility by coupling our probabilistic sampling with News and NeuralAngelo and showing that it improves 3D reconstruction and rendering. In this work, we propose the following pipeline to utilize the SDF for a more effective sampling while training the neural volume field. We start by leveraging the SDF representation to define a probability density function over the points in the 3D scene to capture the likelihood of it being sampled. Then, we explore a suitable 3D image space for effective sampling in the camera's viewpoint and deal appropriately with concerns arising from view dependency. The final step combines the proposed sampling strategy with uniform sampling to ensure a good representation of the scene's foreground and background. Our interpolation scheme transforms the density estimate P of x to the three-dimensional image space. We approximate it using the Riemann integral of all cells from the transformed scene grid that lies in the image space. Here's an example. The 3D image space is colored red, and the transformed scene grid and respective projected points are colored blue. Suppose we want to compute the probability of a point U, defined by the orange-colored cell. Then, the probability of U is the sum of the probability densities of all projected scene points that lie inside the cell. Since P of U does not account for occlusions, sampling a projection ray based on the object's geometry alone can result in many occluded samples. To address this issue, we assume that the volume density per cell is P of U, and compute the transmittance by accumulating the radiance weighted by the volume densities for cells along the ray using equation 1. Using the transmittance, the view-dependent probability is given by equation 2. For pixel sampling, we combine uniform and guided sampling strategies. Our proposed sampling using the view-dependent PDF is better for the foreground, while uniform sampling is better for the background. The proportion of samples sampled by each strategy can be regulated. Besides the losses utilized by each backbone, we introduce 3 losses. The first loss accounts for near-surface samples during ray sampling. For points in the empty ray space, we introduce a loss to encourage small SDF values and exploration. The third loss accounts for rays that do not intersect foreground surfaces. All losses are averaged and the total surface loss is computed using equation 3. We use News and NeuralAngelo as backbones to evaluate our method. This first example shows a mesh obtained using News with our method. Image synthesis quality is kept against the baselines. However, the normal synthesis shows a better reconstruction quality and better separation between foreground and background. Since object quality improves, we show that our method obtains sharper edges and better surface accuracy against the baseline, as seen in the owl's feathers. To conclude the presentation, in this work, we explore the scene's implicit surface representation to define a novel sampling strategy for training implicit neural surface fields. We propose a view-dependent and occlusion-aware 3D orthographic projection space, where image coordinates and depth for each camera are conditionally sampled. Our strategy can be coupled with typical image sampling of neural surface pipelines and does not rely on specific backbones. Thank you for watching. For any questions, feel free to contact us.